In the present discussion, we have to talk about curvilinear coordinates. For that, we should be familiar with the Cartesian coordinates first. In Cartesian coordinate system, we are using x, y and z axis. If you want to specify an axis, we should know the intersection of two planes. Here xy, yz and zx are the three planes. In the xy plane, the value of z is equal to 0. In the yz plane, the value of x equal to 0. In the zx plane, the value of y equal to 0. If you want to specify y-axis is the intersection of xy and yz planes. If these two planes are intersecting, we can specify this axis. If you want to specify z-axis, you should know the intersection of yz and zx planes. We do this in the Cartesian coordinate system. The intersection of two planes specifies an axis. For example, intersection of xy plane and yz plane is known as the y-axis. So the y-axis is specified only with the intersection of xy and yz planes. If you want to specify z-axis, you should be familiar with the intersection of yz and zx planes. If you want to specify x-axis, you should know the intersection of zx and xy plane. If I say xy plane, automatically the value of z is equal to 0. If you say yz plane, the value of x equal to 0. In zx plane, the value of y equal to 0. We need not restrict ourselves to the plane surfaces to define the coordinate axis. Here, to specify an axis, we need the intersection of two planes. Without this form, we may introduce the coordinates in some other way. That is our curvilinear coordinates. Any suitable set of three curved surfaces can be used as reference surfaces and their intersections as reference axis. Such a system is called a curvilinear system. Let us denote the curved coordinate axis by q1, q2 and q3 respectively. It should be noted that the q1 axis is an intersection of two surfaces, q2 equal to constant and q3 equal to constant. The intersection of these two surfaces gives q1 axis. If you want to specify q2 axis, the intersection of q3 equal to constant, q1 equal to constant is taken. If you want to specify q3 axis, the intersection of q1 equal to constant and q2 equal to constant is taken. That's the meaning for this and so on. See here, q1, q2 and q3 are three curved coordinates. The q1 axis is an intersection of two surfaces, q2 equal to constant and q3 equal to constant. q2 equal to constant, q3 equal to constant. These two surfaces are constant surfaces, but here x equal to 0, y equal to 0, z equal to 0. So to specify a coordinate, we need the intersection of two constant surfaces. Here B1, B2 and B3 are base vectors. Now we have to make our transformation from Cartesian coordinate system to this curvilinear coordinates. For that, write down the Cartesian coordinates. X equal to x of q1, q2, q3. Y equal to y of q1, q2, q3. Z equal to z of q1, q2, q3. These are all transformation from Cartesian coordinates to curvilinear. Now we have to write the inverse transformation. The inverse transformation equations are q1 equal to q1 of xy z, q2 equal to q2 of xy z, q3 equal to q3 of xy z. Now we have to define a base vector. Bi. Base vector Bi is drawn in the direction of position vector. Change of position vector R produced by a small change in coordinate qi. So here Bi equal to dou r divided by dou qi. Here I equal to 1, 2, 3. The base vector Bi is drawn in the direction of change of position vector r produced by a small change in the coordinate I. With respect to the change in the value of I, that is qi, then the r value is changed. Suppose I equal to 1, q1. With respect to the change in the value of q1, the position vector r is also changed. That is called the base vector. The base vector need not be a unit vector. The base vector need not be a unit vector. Now we have to write the base vector in terms of unit vector. Dou r divided by dou qi equal to some quantity hi into ei cap. Here hi equal to modulus of dou r divided by dou qi. Now Bi equal to dou r divided by dou qi inside the modulus into ei cap. The unit vector ei cap is equal to dou r divided by dou qi divided by modulus of dou r by dou qi. This is the value of unit vector. Now bi equal to dou r divided by dou qi. This is our base vector. We have expressed this in terms of dou r divided by dou qi into ei cap, which is equal to hi into ei cap. Here hi equal to modulus of dou r by dou qi, then ei cap equal to dou r by dou qi whole divided by modulus of dou r by dou qi, not ri, dou r by dou qi. Now we know the position vector r equal to I into x plus j into y plus k into z. This is in Cartesian coordinates. Now bi equal to dou r by dou qi, that is I into dou x by dou qi plus j into dou y by dou qi plus k into dou z by dou qi. Dou by dou qi of r equal to I into x, j into y plus k into z. Therefore we have expressed bi in terms of Cartesian coordinates. This is equal to this hi into ei cap. Now we should write the value of bi dot bi, which is equal to dou x by dou qi whole square plus dou y by dou qi whole square plus dou z by dou qi whole square, which is equal to hi square. bi dot bi means I dot I 1, j dot j 1, k dot k 1. So we can get this value. Here ei is our unit vector. So hi ei dot hi ei equal to hi square. Ei dot ei equal to 1. From this the value of hi equal to dou x by dou qi whole square plus dou y by dou qi whole square plus dou z by dou qi whole square inside the root. This is the value of hi. In order to define the coordinate system, the three surfaces q1 equal to constant, q2 equal to constant, and q3 equal to constant must be non-coplanar. Non-coplanar means they are not in the same plane, they are in the different planes. This means that the base vectors must be non-coplanar. Therefore b1, b2, b3 equal to inside the determinant dou x by dou q1 dou y by this is dou q2 by dou x by dou q2 dou x by dou q3. Here dou y by dou q1 dou y by dou q2 dou y by dou q3. Here dou z by dou q1 dou z by dou q2 dou z by dou q3 is not equal to 0. This is the condition for coplanar. The base vectors b1, b2, b3 non-coplanar. This is modified as the simple form. This determinant is called as Jacobian determinant. The determinant is known as Jacobian, and the simple form is dou of x y z divided by dou of q1 q2 q3 not equal to 0. This is a simple form. In Cartesian coordinate system, the smallest distance between the 2 points is dr square is equal to dx square plus dy square plus dz square. In this way we can write the smallest distance between the 2 neighboring points. Here we have to add neighboring points. dr square is equal to dx square plus dy square plus dz square. Now we have to express this in terms of our q1, q2, q3. For that we have to write dx equal to dou x divided by dou q1 into dq1 plus dou x by dou q2 into dq2 plus dou x by dou q3 into dq3. In the same manner, dy equal to dou y by dou q1 into dq1 plus dou y by dou q2 into dq2 plus dou y by dou q3 into dq3. Then dz equal to dou z by dou q1 into dq1 plus dou z by dou q2 into dq2 plus dou z by dou q3 into dq3. See, these are the values of dx, dy, dz. Now we should find out the value of dr square. dr square is equal to summation over hij dqi dqj. Here the condition is hij equal to 0 if I not equal to j. hij equal to 1 if I equal to j. Then I equal to 1, 2, 3. This is the value of dr square. Now the condition is the value of hij equal to 0 if I not equal to j. If I equal to j, then the value of hij equal to 1. Then dr square is equal to dqi dqj. Now we will verify this. See, dr square equal to summation over hij dqi dqj. If I equal to j, hij equal to 1. This is the condition. If I not equal to j, hij equal to I not equal to j, hij equal to 0. Here the value of hij equal to dou x by dou qi into dou x by dou qj plus dou I by dou qi into dou I by dou qj plus dou z by dou qi into dou z by dou qj. This is the value of hij. If I give this condition, dr square is equal to summation over I comma j, hij of dqi dqj, the value of hij should be this much. If I equal to j and I equal to 1, 2 and 3, hij equal to 1. Now apply this condition. hij equal to, first take the value of I equal to 1, I equal to j equal to 1. We make it dou x by dou q1 into dou x by dou q1 plus dou I by dou q1 into dou I by dou q1 plus dou z by dou q1 into dou z by dou q1. Next condition, I equal to j equal to 2. This is summation. Here we have to put I equal to 2. Apply the second condition. Dou x by dou q2 and dou x by dou q2, because I equal to j equal to 2 plus dou I by dou q2 into dou I by dou q2 plus dou z by dou q2 into dou z by dou q2. Next apply the condition I equal to j equal to 3 plus dou x by dou q3 into dou x by dou q3 plus dou I by dou q3 into dou I by dou q3 plus dou z by dou q3 into dou z by dou q3. This must equal 1, because if I equal to j, hij equal to 1. This is summation. Now this is modified as dou x by dou q1 square plus dou I by dou q1 square plus dou z by dou q1 square plus dou x by dou q2 square plus dou I by dou q2 square plus dou z by dou q2 square plus dou x by dou q3 square plus dou I by dou q3 square plus dou z by dou q3 square equal to 1. If I equal to j, summation of dqi dqj equal to, first put I equal to 1, dq1 into dq2. This is summation. Put up the next value. here dqi dqj. If I equal to j, take I equal to 1, you can get dqi, then dq1 into dq1. Next, I equal to j equal to 2, dq2 into dq2. Then I equal to j equal to 3 plus dq3 into dq3. This is equal to dq1 square plus dq2 square plus dq3 square. Therefore, put up all these values in the equation. Dr square is equal to summation over hij into dqi dqj. If I equal to j, summation over hij equal to 1. See the previous case. Here, if I equal to j, then these are all the values. If I put I equal to j, all the values are equal to 1. If I equal to j, the value of dqi dqj equal to dq1 square plus dq2 square plus dq3 square. Dr square equal to dq1 square plus dq2 square plus dq3 square. But in Cartesian coordinates, the value of dr square is equal to dx square plus dy square plus dz square. Whereas in curvilinear coordinates, the value of dr square is equal to dq1 square plus dq2 square plus dq3 square. Therefore, we may write the value of dr square is equal to summation over hij into dqi dqj. If you use this condition, we can get the value of dr square equal to dq1 square plus dq2 square plus dq3 square. Here hij equal to 1 if I equal to j. hij equal to 0 if I not equal to j. If you apply these conditions, here I equal to 1, 2, 3. We may have the value of dr square is equal to dq1 square plus dq2 square plus dq3 square. Whereas in the case of Cartesian coordinates, dr square is equal to dx square plus dy square plus dz square. This is the smallest distance between the 2 points in Cartesian. This is the smallest distance between the 2 points in terms of curvilinear. Here x, y and z are replaced by q1, q2 and q3. Therefore, this is the necessary condition for making the transformation from Cartesian to curvilinear. Now we may say that the base vectors b1, b2 and b3 are not perpendicular to each other. Therefore, these are not orthogonal curvilinear coordinates. These coordinates are not orthogonal because the base vectors q1, q2 and q3 are not perpendicular to each other. This is non-orthogonal. Because the base vectors are not mutually perpendicular to one another. Now see this, the base vectors B1, B2 and B3 are not mutually perpendicular to each other. Therefore, they are not orthogonal curvilinear coordinates. They are mere curvilinear coordinates.